Okay, this is a continuing 3.3 from yesterday. So we're going to keep talking about linear functions in discrete and continuous. So we've got two different types of domains that you can have. So there's discrete and there's continuous. Discrete is a set of inputs that have certain numbers. Okay, so if I had, let's say, 0, 1, and 2, and 3. So discrete are just a set of those. They're not included in everything between. So like, let's say I have 0 included and 1 included and 2, let's say. And I don't have 3. So those are the 3 that are included. I don't have 3, and then I don't have anything between. So like 1.5 wouldn't be between it. It would just be 0, 1, and 2. And you would kind of write it like 0, 1, and 2. So that's how you would write your domain in that way. Continuous is kind of in the word, so it's still a set of inputs that consists of all the numbers in a certain interval. Okay, set of inputs that consists of numbers in that certain interval. So let's take that exact example. We have 0, 1, 2, and 3. So in this case, if I have 0, 2, 2, it includes everything between it. So it would be between those. So you would say like from like 0 to 2, that little dash between it can show that it is included in all. So those are the two different types of domains that you can have. So we did the first 3 examples yesterday, so jumping into example 4. So we've got the linear function, y equals 15.95x represents the cost in dollars, and then of X tickets for a museum. So they always will explain kind of which one is which is going to be important in the context. Each customer can buy a maximum of 4 tickets, okay? So we're going to find the domain of the function. Is it discrete or continuous? So in the context of the situation, you kind of ask yourself, is it going to be just 0, 1, 2, 3, and 4, or can you get tickets from 0 to 4? So in this case, X must be a whole number. Okay, if you are buying tickets, you can't have 1.5 tickets, so it must be a whole number. So the domain is discrete. Okay, so our domain would include 0, 1, 2, 3, and 4. And when it says maximum of 4 tickets, you could also get 4 tickets. So those are the 5 different options that you can get for that. If I were to graph the function using its domain, so right now I only have positive X and Y. There is no way that you can have a negative ticket. So I feel like that would be number 1 to do. When we are doing domains, we can kind of pick our own inputs and then see what kind of outputs come out of it using the equation that we have. So in this case, I'm going to use the inputs that I have. So I've got 0, 1, 2, 3, and then I'm going to do one more, and I got 4. And then we're going to separate them. Okay, so we're going to input them using our equation. So our equation in this case is y equals 15.95x. We are going to use that to plug it in. So I'll show you the first one, but I feel like it will make sense when I plug it in what you're doing. So we've got 15.95 times 0. And then you see what is your output when that happens. So when you plug in all those numbers, what do you get? So obviously 0 times anything is going to be 0. And then if I am graphing it, I just need an XY point. So X always goes first, Y always goes second. Sorry. So that means my first one is 0, 0, which makes sense. If I have 0 tickets, it should be $0. Okay. So if I were to plug in all those, that means I'm doing this one. I'm going to do 1, plug this in. I get 15.95. So that means my point is going to be 1.1595. Okay. If I keep going with this, I can do this all the way up to the 4 tickets. So plugging in 2, I'm going to plug in 3. And then I'm going to plug in 4. And then unless told, you don't always have to do a table every single time, but just keep in mind there will be times you have to make your own table, so know how to kind of set this up. So if I times that by 2, I get 31.90. So that means 231.90, so 2 tickets is that. And then I've got 47.85, 3 47.85. And then plugging in for 4, You get 6380. 4, and then 6380. Okay, so those are the points that I'm going to graph on these. When you are doing a graph, couple important things. So labeling them and numbering them correctly. So number one thing is labeling which one is which. NA told us Y is dollars and X is tickets. That's exactly what I want to label this. So dollars for my graph, and then we've got tickets for my X. Okay, so tickets are decently easy. It only goes up to 4. Depends on how you draw your graph. I'm not even going to use the numbers on here. I got 0 here, and I'm going to skip every single one. So 2, 3, and 4. Okay, so those are the only X's that I can include. It's going to go up by the same amount every single time. Okay, other thing, we've got our Y's here. So I have to make sure all of my Y's can include in this graph. So 0 is my smallest number, and then 6380 is gonna be my biggest. So however you do this, you just have to make sure you include all of that, okay? So let's say if I go, I think I can go by 10. So 10, 20, 30, 40, 50, and then I'm even gonna include 60 right here, and then it will be above 60 in that way. Okay, so your graph has to go up by the same amount every single time. You cannot just use what it goes up by, like these ones, because depending on if it's discrete or continuous, sometimes it has to include in between. And in this case, it is discrete, so I know it's not going to be connected. However, just keep that in mind when you're making a graph. So my first one is 0, 0, and then I've got 1, 1595, so it goes right in between this and a little above. 2 is 3190. 3 is 4785. That'd be a little bit closer to 50. And then 4 is 6380. So it's going to be above 60, kind of up there. Okay. When we talk about discrete, I do not want to connect those dots in any way because we cannot have between the tickets. So that would be what your graph looked like if it was a discrete example. Example 5, we got an anteater consumes about 35,000 insects each day. Kind of crazy. Explain why the number of insects consumed is a function of the number of days. So essentially, it's like what kind of, is it going up by the same amount every single time? Is it linear? Is it constant? Is it not constant? Does it depend? So we're kind of explaining what that means first. So if I've got $35,000 each day, I'm essentially saying what's happening over time and is it about the same every single time? So obviously each day, the days increase every single day. So is the function of number of days? It's like yes. So the number of insects increase each day by 35,000. Okay, so that means that rate is constant. So we're gonna have a linear graph. Now, obviously it's not going to be exactly 35,000 insects every single day, but if you are doing something over time, and we're in this case, we're just gonna pretend that it's always that, it's gonna be a linear graph. I know it could be slightly off, but it's essentially that every single time. If I'm talking about the domain, so finding the domain of the function, is the domain discrete or continuous? So can it eat 1.5 insects each day? That's kind of what we're asking ourselves. Can it include the numbers that are between? I would say yes. I know it's maybe unlikely, but I would say definitely you can eat half of an ant or something like that. So I would say days have to be over 0. Okay, so if I'm talking about domain is my X, the thing that I choose, so every single day, and then the insects are the things that can be continuous. So I can have it include everything. And so we're gonna use a sign that shows that anything that is greater than 0. So if I have, let's say my days, in this case, days have to be greater than 0, and it's continuous. Okay, so both our days and our insects, you can have half a day or half an insect. So I feel like either way it's continuous. So I'm going to use that greater than or equal to sign. So that includes all of my days greater than or equal to 0. Okay. Graphing the function using the domain. So in this case, difference in the other one is we've got a continuous graph. So it doesn't necessarily go up by the same amount every single time, but for this case, we're just going to pretend it does. It's $35,000 or 35,000 insects a day, excuse me. And so it is going to be linear and it is going to be continuous, so it's going to connect. So if I was making my graph in this case, I've got my input and then my output, and then you could put the point here too, and then plug in those in. So for our graph, we can just do a couple days. It doesn't have a distinction of how long, many days. I would say just do a couple so that you can see the trend that is happening. But one important thing is it can't be below 0. So we're going to do 0, 1, 2, and 3. Okay, if I plug in 0 to my equation, so in this case, so essentially if I'm writing my equation, it's like saying y is equal to 35,000x. So every single day that is going up by 35,000. So there would be my equation that I would be plugging in for. So if plug in 0, we get 0, 0 again. If plug in 1, you get 35,000. So 1 is 35,000. And then 2, we've got 70,000. And then 3, we've got 105,000. Okay, so graphing these out. Same thing with using a graph. Make sure you label it and make sure the numbers go up by the same amount every time. So in this case, we're going to do days. Same thing as before. I'm just going to skip 1, kind of cross those lines out. So I got 1, and then 2, 3, and 4. So I know we only did 3, but I just put those up so you can kind of see the trend of what will happen in this case. In this case, I feel like you can go up by 35,000 every single time. So if every single one goes up by 35,000, that's totally okay. You just can't have this jump be bigger than everything else. So let's say I started at 35,000. I'm going to put K next to it. So then I can go up by 70K and then 105K. And then if you wanted, you could put the next one, which would be 140K. Just to kind of show the trend, we can kind of see what would be on that 4th day. So we got 0, 0. We've got 155, 70, 3 is 105, and 4 would be this one. Okay, so we kind of see that linear trend, the arrow to keep going up as the days go up, and then you do have to connect them because it's continuous, because it can be between the days and it can be between insects. All right, last example. Kind of looking at 2 different graphs and being able to see what kind of situation am I looking for with a discrete one and a continuous one. So we're going to write a real life problem to fit the data shown in each graph. Is the domain of each function discrete or continuous? So I feel like the easiest part right away is kind of saying which one's discrete and which one's continuous. So this one would be discrete. Guys, spelling is not my thing. X is whole numbers, so that is why we know that. It's not connected, it's whole numbers, it can't be between those two. And then this would be continuous. So X can be numbers from 0 to 6, like anything in between that. So like it's included in all of those X values. And so that would be why that is continuous. Okay, so if we think about what is a real life situation that I would use for both these graphs. So obviously there's not one perfect answer. You can try to think of it, kind of a couple examples of why this would be discrete or continuous. So I would say maybe a couple examples of discrete, like a game show and questions. Okay, if I was on a game show, I can't be asked like 1.5 questions. I could be asked each question, and these are the point values. So questions and point values. That would be a good example of that one. And then, so continuous, anything from 0 to 6. So let's say we've got like a biking. Let's say the X is hours, so biking, so we've got X is hours. And then we've got Y is miles remaining. Okay, so if I've got X hours and Y miles remaining, I can obviously bike for 1.5 hours, and then I've got miles remaining. It is going down in this case, so obviously it wouldn't be going up. Like if I started at 60 miles at 0 hours, and then at the first hour it goes down to 50, and then it keeps going down by that. I can include everything in it, so that would be a good example of that. That's not the only example, but just so you can kind of get a picture for what that looks like. Okay, and that's it for today.